Hi everybody, welcome back here, and even if you're new to this channel, thank you for clicking on this episode. Today we're going to continue our discussion about several web-related attacks and mitigation techniques. Now, we still have a couple more to cover, and among these, a few of them have something in common, and that is session management. So what is a session? Now, to keep the story short, a session is just a piece of information. Most of the time is just a randomly generated very large number, which is generated by the web application, by the website, whenever you first interact with it or when you first log into that website. It's stored on the website as well as in your browser. And it is used to uniquely identify you as a unique user across all kinds of interactions that you're performing on that website. Sessions are what makes it possible for you to authenticate just once to Gmail or to Amazon, and then any subsequent requests that you send to that website, like searching for a product, sending an email, adding something to the shopping cart, placing an order, checking your email, all these actions can be tied to your account. So a session is also something that keeps you from seeing somebody else's shopping cart, from accessing somebody else's email, or from accidentally ordering something from Amazon and delivering it to somebody else's address. And we can also use this unique identifier, the session identifier, to connect your identity to some other piece of information that might be stored on the website. For example, your profile settings or the contents of your shopping cart. So basically, once you're authenticated to a website, the session information becomes somewhat like a unique password generated just for you, just for your account, and perhaps even just for a limited amount of time that allows you to interact with that website even further. Now, since the session information is the only thing that identifies you as a valid user of that website, this information must be protected, because whoever has access to that session information can impersonate you, because that's the only thing that is required by the website, a valid session ID. If you present a valid session ID, then any actions that are allowed on the web application by the user that matches that session ID are going to be executed, are going to be accepted. So with a stolen session ID, somebody can post on Facebook on your behalf, can send emails on your behalf, or order stuff from Amazon on your behalf. Okay, so how is this implemented in real life? Well, if we're talking about web applications, we're basically going to talk about the HTTP protocol. And the problem is that the HTTP protocol was designed from the very beginning to be stateless. That is, we have no method of storing persistent session-related information in our HTTP requests. Though the HTTP protocol was designed so that one request would have absolutely nothing to do with the next request. That's stateless. There is no state information in those requests. So we invented something new, and that something is called a web cookie. Now, the cookie is just a small piece of data that is generated by the web server, and it's sent along with the response header. So when the web server responds to you, then it's going to also send you, this is the cookie that I've generated for you. Then it is expected from the client browser to include this cookie information on all subsequent requests that it sends to that website. And having the same cookie information in all future requests makes them belong to the same user session as far as the web server is concerned. So as long as the web server keeps seeing the same cookie value in a series of requests, it can determine that all those requests come from the same user, same computer, same browser. Now, if the cookie information is missing, or you're sending the wrong cookie information, then the server is going to behave like it doesn't know who you are. So it's probably going to redirect you to the login page or simply give you an error. And by the way, we can also have non-persistent cookies, which are just stored in the browser's memory, or persistent cookies that are stored in your browser's cache, so on your disk. You've definitely seen persistent cookies in all those websites where you have on the login page, you have a checkbox for remember me or remember my user login for next time. That option tells the web server to generate a persistent cookie that is being stored in your local cache, and then next time you visit the same website, you're simply going to be sending the same saved cookie and not go through the entire authentication process again. And those are also the cookies that get deleted whenever you delete your personal data or your browsing history when you check cookies in your browser as well. Okay, so cookies kind of work like passwords, right? So we have to secure them, right? And well, I don't think I need to mention that securing cookie information in transit while they are being transferred to your browser should be done just like like with any other kind of sensitive information, mostly by using TLS, so Transport Layer Security, using HTTPS when talking to the web server. But remember that even a TLS encrypted cookie is still a clear text cookie when it gets stored in the browser's cache. So encrypted cookies at rest, encrypting the contents of the cookie, is up to the application developer. Anyway, there are a couple of cookie attributes that you can look after as best practices when securing web applications. The first one is the secure attribute. This one tells the web browser to only send that cookie information to the web server if the connection is a secured one, so if it uses HTTPS. Next one, HTTP only. This is another attribute that is very useful at preventing a type of attack that we'll be covering in the next few minutes, which is called Cross-Site Request Forgery. Now, before we get there, the HTTP only attribute is going to prevent access from client-side scripting to that cookie's contents. In other words, a JavaScript that's running in your browser is not going to be able to access information from that cookie, which is useful because JavaScript code could be malicious. Same site, another useful attribute because it requires the request, the HTTP request itself, as well as the cookie to come from the same website name or website domain. This is very useful against fighting those bogus requests created or forged by attackers from different websites. And finally, we don't want to let cookies live forever because that's sensitive information. The longer we store that information, the higher the risk of it being compromised. Now, what happens when a cookie expires? Well, you can probably guess. It happens just like the first time you visit a website, right? You're going to go through the authentication process, and if you successfully pass authentication, then the website is going to generate a brand new cookie for you with a new expiration timer. Okay, so we have sensitive information stored in those cookies, and we're at a cybersecurity training. So the next question should be, how do we steal this information? Well, the official term for this is session hijacking, which is basically just a method of taking over somebody else's session without them knowing about this. What's the purpose? Of course, to impersonate that user and send requests on their behalf. Now, how can this happen? Well, the most common way is to just intercept that session information when it is being transmitted to the user. This requires an attack along the lines of a man in the middle. So you need to intercept that traffic, be able to decode it, and be able to see that session information and then reuse it in your own requests. Less common, but just as dangerous, is by using a compromised browser. So a browser that has been hacked, that has been compromised by an attacker, has the ability of course, revealing what information it receives when communicating with a website and potentially sending this information to an attacker, including your passwords and your session information. Another method, which this time is also related to a programming error, might be about a bad algorithm for generating those session IDs, those cookies. Now, if the generation algorithm is so bad that the cookies it generates can be predicted, then, well, there isn't much need for session hijacking at all, is it? Basically, if an attacker can predict one or more session values, it can take over a session that hasn't even been established yet. That's why I said at the very beginning that those session IDs are usually very large, randomly generated numbers so that they cannot be predicted. And we can also think about other bad programming practices, like exposing that session ID right on the website, or in the URL, or on the user's profile. Simply because the programmer doesn't know that the session information is sensitive information. Now, you might think this is trivial. You would be amazed how many websites make this mistake. So generally, best practices dictate that session generation should be firstly non-predictable, and secondly, well, we need to ensure that the sessions expire and require re-authentication after some time, after a certain time span. Another term and attack type that you might encounter is called cookie poisoning. Now, cookie poisoning refers to an attack that attempts to change the content of a cookie after it was generated, in an attempt to send that altered cookie to the website and then use it to exploit some vulnerability in that web application or that web server. So it can even translate into a method of performing code injection through a malformed cookie. How do you defend against this? Well, validate your input. The cookie is also a type of input because you're receiving it from your users. Make sure that the cookie contains only expected values, not executable code, for example. And perhaps even implement a mechanism that can ensure that the cookie hasn't been tampered with, because there shouldn't be any changes performed to that cookie from the original version that was generated on the web server. the client has no business changing that session value. Of course, don't forget to encrypt them whenever you store them or whenever you transmit them. And also, remember to delete those cookies from the cache automatically or manually from time to time, or whenever the client terminates the session. That's the logout functionality. Now, I know most people don't use the logout functionality, but make sure it's there and that it does what it's supposed to do. That is to clear cookie information from the web server. You don't need to worry about cookie information on the client side, because as long as the cookie on the client side has no corresponding match on the web server, then it's simply just a useless value. So let's see an example of how badly generated session IDs can look like. Now on this web page here, it says that it will generate a new cookie called DVWA session each time this button is clicked. And you're not going to see anything happening because the session information happens in the background, but we can see that session value if we open developer mode. So we'll head over here to the network tab and then click it one more time. Now the first one here you can see has a status of 200 and it's of type document. That's the one that we're interested in. And this is going to be the main page that comes as a response from the web server. Now right here in the response header section, we can see that the set cookie parameter points to a DVWA session equals 4458. Now let's click this one more time. I'm going to click generate again. Head over to the first document here. You can see this time is 4459. Generate again, and as you can expect, this time is going to be 4460. So the session information is just a simple consecutive number. This is very badly generated because anybody can predict what the next session is going to be and even try to guess a valid session that has already been generated. Now you can see that the security level of this vulnerable web application is currently set to low. So let's increase it just a bit. I'm going to set it from low to medium. We'll go back here to weak session IDs. And let's try to see how those session numbers look like now. I'm going to click generate again on the network tab, first document, and the DVWA session is now a longer number, a more complex number. Is this random or not? Now this kind of looks more promising, right? It looks like a number that we won't be able to just guess, or can we? Now to better understand just how random that value really is, we're going to use Burp Suite. So under the proxy tab, I'm going to set interception to on and then click generate one more time. And as we expect, we can see that same cookie value here at the bottom. So this is our request that we're sending towards the web server, and we're including this cookie as well. We can, however, take this entire request and then send it to sequencer. Head over to the sequencer tab and then start the live capture. And as you can see here by the number of the requests that is still increasing, the sequencer is going to send a bunch of requests and then analyze how the responses to those requests differ from each other. How much randomness is in the responses that we received from the web server, which is a great way of determining if that unique value that's supposed to be the session ID is random or not, right? We're going to stop it right here because we already have enough requests, and I'm going to click Analyze Now. As you can see here, the overall result says that the randomness within the samples is estimated to be extremely poor. Why is that? Well, there's a very simple explanation to this. That session ID is not a random value. But what is it? Well, we can try to figure this out. First, let's stop the sequencer here. Let's go back to the proxy tab and then copy this value into our clipboard and head over to the command line. Well, one thing I can do is to paste this within the date command and try to decode this as a timestamp. And apparently that seemingly random number, it's actually a timestamp. Actually, it's the Unix epoch time, so it's the number of seconds elapsed since the 1st of January 1970. As you can see here, the time that is encoded in this number right here is at the actual time right now, at the time of this recording. So again, this is a bad session ID generation algorithm. Anybody can guess the right session ID simply by looking at the time. Let's increase the difficulty just a bit more. So let's head over to the vulnerable web application, turn intercept off, and then increase the security level to high. All right, now the security level is set to high. Let's go back to weak session IDs Click the generate button a couple of times here, start developer mode, move over to the network section, and then click generate again. Right, we're gonna head over to the first document, header section, and this time we're gonna find that the set cookie right here points to a DVWA session with this value. Now, as you can see, this is no longer a timestamp, this is hexadecimal, but what does it look like? Does it look like something familiar to you? What if I told you that this right here has 128 bits? Don't trust me? Just count the letters here, multiply by 4, and that's the number of bits. You're gonna find 32 characters in this string right here. That's because this is an MD5 hash. Let's see if we can reverse this hash. To do so, we'll head over back to our command line right here, and I'm going to use the hashcat utility just like this. Now, the hashcat utility can be used as a brute force password cracking program. What we're going to do here is we're going to use it using an attack method of 3, which means brute force. -M, that's going to be the hashing algorithm. In our case, 0 means MD5. This one here is the hash that we just copied from the HTTP request, and this is a pattern here where we expect to find as a result a number of at most 4 digits, right? Just to keep this simple. Let's leave this for a couple of seconds here to run, and we're done, right? It took less than 1 second actually, and if we scroll back up here, we're going to see that the equivalent for this hash is this number right here, number 5. So basically what we have right here, and we think that this is a unique random value for the session identifier, is nothing else than a simple MD5 hash of a sequential number. This is the 5th time I've clicked the generate button, and this is the MD5 hash value of number 5. For number 6, for number 7, for any future session ID, I can easily guess the right value here simply by performing the standard MD5 hashing algorithm. So even though this looks random, it is not. And actually, we can even fool some penetration testing tools like Burp Suite using an algorithm like this. Let's turn on intercept. Let's click generate one more time. It's going to get intercepted by Burp Suite. Let's send this again to sequencer. Let's remove the old one. All right, and start a live capture. I'm going to generate a couple of requests here. Let's click on stop and then click analyze now. And as you can see, the overall result is that the randomness of the sample is estimated to be excellent, but it's not, right? It seems like it's a random value, but at a closer look, it's just an MD5 hash of a simple sequential number. So careful with this. Many web applications use this method to seemingly generate random session IDs. If it looks like an MD5 hash, if it looks like a SHA hash, then it might be so easy to crack, to guess the next session number and to impersonate some other user. Alright, next up on the list is Cross-Site Request Forgery, sometimes abbreviated XSRF as well. So what is this? Well, this is an interesting one. It's basically kind of an exploit for cookie-based web applications, which also implies just a bit of social engineering. So what do we have here? Well, we have a valid website on the right. It might be a bank or whatever website. We have an attacker on the left, and they also have their own website. And then that's you in the middle, your victim's browser, your computer. So what happens here? Well, one day you just decide you want to visit your bank's website. You just legitimately visit that website, you authenticate, everything is good, and you leave that website open somewhere in a tab in your browser and you forget about it. And at some point during that day, you receive an email, you receive an instant message, maybe you see a forum post with an interesting link, and you decide to click that link. Now that link is going to point you, unknowingly, to an attacker's website. Well, the attacker's webpage might also include a piece of cross-site request forgery code just like this. What's in this code? Well, it's a simple web form that, as you can see, points to your bank's website and to its transaction page, and also includes some hidden parameters in there. One of them being the destination account, perhaps the currency, and perhaps the money amount that is to be transferred. So in our case here, it's going to be $2,000 to be transferred into the attacker's account. And the last line here on the screen is a small JavaScript code that simply submits this form automatically the moment you visit that web page. So you're already logged into your bank's website. And now The browser sees a request that is supposed to be sent to that valid website. Nothing wrong here as far as the web browser is concerned. What happens though is that you're basically going to be sending a request, a money transfer request, to that banking website where you're logged in without even knowing about it. This right here is an example of cross-site request forgery. So an attacker is basically forging or faking a request to a valid website where we have a valid account with valid login without our knowledge. Now, since you're already logged in, well, the banking website has a valid session identifier for you. That session identifier is going to be used in this request just like in any other request that might be initiated by you. And chances are that the request is going to be processed by the website because the website knows that the request came from your browser, from an authenticated session, but it doesn't know that you are not aware of it. That's the tricky part of cross-site request forgery. And if you think about it for a second, we can use this method for a large number of attacks. Not just, fraudulent money transfer, but we could also instruct the web browser to download a piece of malware. We can send such a request to a colleague in the HR department because we know they are always logged in into the payroll application, for example. And we can trick their browser into forging a request that makes changes in the payroll application. We can even send such a request to the finance or accounting departments, knowing that they're always logged in into the invoicing application and, create fake invoices on their behalf. The possibilities are endless. So how can we protect against this? Well, as the browser is the main actor here, the main component that's involved in this attack, unfortunately, there's not much we can do on the browser side, because as far as the browser is concerned, that's a valid HTTP request generated by valid web page code. The browser has no way of figuring out whether you are aware of that request or not. So let's see how we can fix this time on the server side, the web application side. Now, the main method of securing against cross-site request forgery is by using CSRF tokens. Now, these are very similar to session variables that we just saw in our cookies, but this time we're generating some random values that we're embedding within the HTML forms on the website. So the moment you submit an HTML form in a web page, you're also going to submit that cross-site request forgery token. And of course, it has to match. Now, this also means that if the same form is being submitted automatically by some external code, some external malicious code from another website, that code will have no way of knowing what that CSRF token is. So the request coming from a different web page is going to be ignored. These tokens can be generated for the entire session, so right after you log in into the website, or even per page. So every time you change your page within a web application, you can get a different CSRF token generated for you. And those are websites where you see that the back functionality doesn't work that well, or even doesn't work at all, because every single page that is generated, including the one that you're trying to go back to using the back functionality in your web browser, is going to be accepted only with a different CSRF token. And once you've navigated away from one page, that token is lost, and that's why you cannot, in some web pages, use the back functionality. Now, of course, be extra careful, don't communicate this token using cookies, because cookies, if not secured properly, can be read by JavaScript code, and some other website might be able to read that value from a valid cookie that is stored in your browser's cache and then reuse it to forge a request to that same website. Now, this method works for stateful applications where we can store on the server that token information. Now, if we cannot store token information on the server, we can use something called a double submit cookie. And I know this kind of sounds like some sort of Oreo cookie, but a double submit cookie is basically a method where we send the same large random value in both a cookie and a hidden input field inside of a form. The server then only needs to see if those two match. Now, of course, since we're relying on sensitive information inside our cookies, then we definitely have to protect our cookies. Another method is by using specific HTTP headers like domain, origin, or refer. All of them are concerned with validating that the request is coming from a valid website address, which is exactly what doesn't happen when we are facing a cross-site request forgery attack. Generally, checking the origin or refer headers is considered to be safer because those two are types of headers that you cannot programmatically change using JavaScript. Only the browser can change those parameters, and we kind of trust the browser a bit more than we trust the code that the browser is executing. Another parameter here, another attribute, is the same site, which instructs the browser whether to send or not a cookie that doesn't match the website it was designed for. Also, you might find it trivial, but CAPTCHAs are also a very nice mitigation technique. At least they warn the user about the fact that they're about to execute or to submit a special type of request. CAPTCHAs simply involve the user, to validate I'm a human, or to, find some pictures of a bike, for example. But they're also a way of making sure that a certain type of request cannot be sent without the user's awareness. And finally, protecting our cookies, just like we described a couple of minutes ago, is going to help, but it's not going to be enough. Because regardless how well we protect those cookies, the browser still has access to them. And if the web application is badly programmed, and even if our cookies are encrypted in transit or at rest, they're still very much usable in a CSRF attack. So just like we saw a couple of minutes ago, HTTP only to make sure that we don't have programmatic access to those cookies, secure to encrypt them, path, which specifies which address or which subdomains or for which website path those cookies are valid, setting expiration timers, of course, requiring re-authentication, and so on. All these methods are going to help you, but they're not going to be enough precisely for cross-site request forgery. And of course, let's see some CSRF in action. Now on this page here, we can change the admin password. So basically, if I just type here, let's say 123 and then 123 to confirm it and click change, now the password has been changed. Have a look at the URL. Or even better, let's just open developer mode again and type 123 one more time. Click document here, and at the very bottom you can see that the query string parameters are password new 123, password conf from confirmation 123, and the operation is change. So basically it's really easy now to craft a specific URL like this in order to trick a user, a logged in user, into changing their passwords without them even knowing. So let's see how we can forge a request like this. Now for this, I just started a Docker container here. So the second one here is running Nginx. That's a very simple and lightweight web server running on port 8080, and it's called Hacked Web. And this web server here is going to host a fake website that I'm going to use to trick my user into accessing it and then performing this cross-site request forgery. Now let's connect inside of this container and see what's the content of its web page. So I'll just go ahead and docker exec inside of this Hacked Web container and launch bash inside of it. All right, I'm inside of container right now. So let's display the contents of index.html that will be presented by whoever accesses this site. And that's going to be located at user share nginx html index.html. And that's the website code, right? It says here, welcome to my completely safe website. And then we have an image tag. But have a look at the source of that image. The source of that image actually points to my damn vulnerable web application. That's the web application where I'm already logged in with a valid request here that says password new equals hacked and password confirmation equals hacked again. All right, so let's see how this looks like in a browser. Coming back here to our victim's computer, we open a new tab and let's try to access that very website. Welcome to my completely safe website. All right, nothing else visible on this page. But if I go back here to the damn vulnerable web application, and let's say I just log out, all right, let's close this developer view as well. And I try to log in using admin and the password hacked. Well, apparently my login just works. I've successfully changed the admin password on this website without the admin even knowing, simply by tricking the admin into visiting an apparently completely inoffensive web page. This is cross-site request forgery. And this is the forged request, right here in the website code. Now, there are a couple of things that you might be thinking now. Well, what if my website parameters are not exposed in the address bar like that? So it's not everything exposed in a GET request. What if it's a POST request? Well, if it's a POST request, then we're back to the first example here on the slide. So in this example, we have a hidden form that gets automatically submitted as a POST request by JavaScript code that gets executed on the same page. So there's no difference between a GET request or a POST request. They can both be very easily used to perform CSRF. On the other hand, you might be thinking, well, how is the attacker going to know which sites I'm visiting, which bank I'm using, which online shop I'm regularly visiting? There's no way to, try every banking website in the world and try to fake requests towards all types of destinations that your users might happen to be logged into. Well, there are 2 points of view here. First of all, remember the fact that the attacker only needs to be successful once. Even if the attack fails 100 times, if it's successful just once, it's still called a successful attack. Secondly, think about the fact that these are much better suited as targeted attacks, where you know exactly the person that you're trying to attack, you know what their habits are, you can probably find out which website the HR department uses to order, pizza or sandwiches at lunchtime, or where a specific manager goes to order, airport transfer. You can target these links with CSRF code in them towards people that, the HR department that has access to the payroll app, or to the finance department that has access to the invoicing app. You can forge valid requests specifically for those applications, especially if those applications are developed internally or just used internally. Probably the security is going to be weak, to say the least. Finally, the last one for today is called Clickjacking. This one is a method of stealing a user's inputs in a web page. So it basically works by changing a link in a web page, or by inserting a transparent layer with an inline frame on top of a web page. This way you can trick a user into clicking a different link than the one intended, or into typing their credentials into a different form than the real one. Of course, the fake form is going to send those credentials to the attacker and not to the real website. How can you accomplish this? Well, you have to find a way to inject additional code into that website. Cross-site scripting is a great starting point. So how do we protect against this? Well, one method to protect against inline frames is called frame busting, and it uses a very short JavaScript code like this one that forces the web page content to be the topmost element in the page. So if it checks whether the web page is at the topmost level, and if it's not, it simply relocates itself to the top location, thus not allowing additional iframes on top of it. This is a basic defense against clickjacking. Now, other measures can be set up using HTTP headers like X-frame options, which can have any of the following parameters like deny, same origin, or allow from, which dictate if and what kind of framed content is accepted on that specific web page. Alright, so we're pretty much done with the web application attacks. Phew, that was a long one. So I really hope you found this informative, useful, and easy to follow and understand. If you did, don't forget to like and subscribe, and hope to see you next time when we talk about privilege escalation and password cracking. See you next time.